So what I would like to talk about this morning is basically something that characterizes our research agenda in the Transport and Mobility Laboratory. We basically conduct two research avenues. One is about modeling behavior, so using mathematics to predict human behavior on the one hand, and on the other hand, we try to optimize. We do operational research, and basically the objective in this project is to merge the two, is to try to include behavioral models into optimization. And the problem is that sometimes behavior can look irrational, so which is a challenge. So what I would like to do this morning is basically to tell you about this irrationality, or at least the apparent irrationality, and to see how we can actually capture this in the mathematical models, and then solve an optimization problem based on this. And I selected a specific problem, the pricing problem, although our objectives are to include these kind of models into any type of optimization problem. Interrupt me anytime if you have questions, if you want to, some more clarifications. Yeah, you can ask questions during the talk. People online are hearing, yeah, everything is fine. Okay, good. So the menu is that I will basically introduce you to choice model, a very quick introduction to choice models, and then talk about irrationality, or at least apparent irrationality. And then we'll look at how we can include these models into optimization. And then I will walk you through the model itself that we are trying to solve when the pricing problem I was talking about. Okay, so the whole idea about modeling choice behavior is based on the concept of utility. So that's a concept which is from the first principles in economics that assumes that human beings are rational. Okay, and what they use as a concept is the concept of homo economicus, which is an agent who is rational and self-interested. And the idea basically is that economists, they assume that people, when they make choice, they actually solve an optimization problem. They want to maximize the utility, whatever it represents to them, in order to make the choice. Okay, so that's basically the first principle from the first course in microeconomics. We assume that individuals solve an optimization problem, which is very appealing for us as we like optimization. The problem is that you don't observe utility in practice. I mean, even people themselves don't even know about this concept of utility. So the way we model it is using a random variable. Okay, so this notation here is the utility that an individual N associates with an option I. So maybe the utility for me to come here by metro or to come here by car, this can be the two alternatives. And for the analyst, this is the combination of something that we can observe, the time it takes, the cost for the trip, and many other things which is in the back of the mind of the decision maker that I will never be able to observe as an analyst. So this is a utility represented by random variables, and therefore what I will be predicting, it will be a probability. So I will predict the probability that I will take the bus or the metro to come here, and this will be simply the probability that this is associated with the highest utility. Okay, so this is the way choice models are made operational using this concept of random utility. The most famous model is called the logic model, and the guy who came up with this got the Nobel Prize actually. So this is one of the famous formula. So basically, it's based on some distributional assumption on these epsilon, so the random variables, and you can use these V. So the V's again are the deterministic part of the utility, the things that you can observe. You plug them in this formula here, and you get the probability. So it's a very simple formula, and it's very convenient to use. Good. The problem is that this assumption that people are rational, we are maximizing this utility, well, sometimes does not seem valid. And this is what I would like to talk about, is that we need to go beyond these models because the main assumption is not always valid. So I would like to show you a couple of evidence of a couple of experiments that people have made that shows that there is some irrational behavior around there. And actually, I will always mention it as apparent because eventually I would like to be able to model this. Right? So this is a first example by actually he got the Nobel Prize as well for all these experiments that he conducted. And this is the experiment. So he asked people to put their hand in cold water for 1 minute. So 14 degrees, it's not very pleasant. I didn't try it, but I imagine it's not present. So this is what they call the short trial. And then they ask to put the overhand, the right hand, this is a long trial, again, for 1 minute at 14 degrees, and then they want us to keep the hand in the water, and they warm it a little bit, all the way to 15 degrees, not big, okay? And then they are asked, okay, which one of the trial did you like the most or dislike the most? And interestingly, most people prefer the long trial. When if you look at it from the pure utility point of view, I mean, in both cases, you have to keep your hands in 14 degrees for 1 minute. But here it's worse because you have to keep it longer. So if you take the utility perspective, the short trial should be more appealing. The reason is that, and this is something that is well known in hospital when they measure pain, when it's about pain, usually duration does not really play a big role. What is really important with pain is the peak and the last moment. Okay, and here the peak is the same in both cases, but the last moment is better because you finish at 15 degrees. And this kind of behavior has been observed in many similar experiments, again, in the context of pain in hospital research. So it means that if we use blindly this utility concept, we will fail in predicting this kind of thing, and we need to take this into account. This is another example. I read it from a very nice book, which is called Predictably Irrational by Dan Ariely. If you like this kind of thing, I really advise you to read this book. It's very well written and very entertaining. And the example that Ariely takes is this one. He saw an ad from the Economist for a subscription to the Economist. And these are the options. So you can have the web only for $59, the print only for $125, and the print and web for $125. And when you see this, isn't it ridiculous? I mean, who will ever buy the print only, right? Because for the same price, you get the print and web. Indeed. So what he did is, okay, let's try. So he did an experiment where he made two groups of people. And in one case, he exposed people to this choice. And in the other case, he exposed people only with the two relevant choices. And basically the outcome, so yeah, that's the experiment. So experiment one, we exposed the ad as it was published by The Economist. And in the second experiment, he removed the irrelevant alternatives. And here, the interesting thing is that, well, as expected, nobody will buy this, so people are not that stupid. But if you look at the share of the other two alternatives, they are completely reversed. So in this case, the majority, like almost 70%, decided to take the web only. And in the other case, it's exactly the opposite. 84 people took the expensive one. So this is something interesting because the presence or absence of something which is actually irrelevant because nobody will ever buy it changes completely the odds. And this is something which is known in marketing as the decoy effect. If you go to some fancy restaurant, you get a wine list and you see some bottles of wine with 4 digits, the price is completely ridiculous. Well, actually, they will never sell this price, these bottles of wine. This is a decoy. But people in the back of their mind say, okay, here, this is an expensive restaurant, so I'm expected to spend more for the wine. And in average, they will spend more for the wine they will buy. And this is something which you see in many contexts. It's called the decoy. Okay, so we have dominated alternatives. And of course, according to the utility theory, it should not matter, right? Because, I mean, if you like better this alternative in this context, you should like it also here because this one is relevant. So again, this is where the pure utility theory will fail to predict. And why does it work like this? Well, it's about the perception. So maybe people are maximizing, but the data they use to solve their optimization problem is different in both cases. The perception they have about the alternatives is different. So we have to take care of the perception. So as I said, this is called a decoy. So in marketing, so this is a high price, low value product, which is compared to the other item in the choice set. And it is used to shift the behavior of consumers to more expensive items. So I took the example of the wine list, but it happens in tourism, in diamonds retail, in tobacco treatment. There are a lot of examples in the literature of this decoy effect. And there is one which is well known also if you go to movie theaters. So this is a very typical cases where you have a small, medium, or large popcorn, but nobody will ever buy this one because for 50 cents difference. So this will again attract people to the more expensive alternative. If you don't propose this, a lot of people will actually buy the small one. It's exactly the same. Okay, and again, this is something which is well known in marketing, and this is something that we need to be careful about, because when we predict, we need to take this into account. About perception, so McFadden is the guy I was talking about, the guy who got the Nobel Prize for the choice models, but he used to make some wine as well. And this example comes from him. So he said, okay, if you ask people to choose between a McFadden red at $10 and a Napa red at $12, well, he's not very well known for winemaking. So most people will say, okay, I will basically buy the Napa because Napa is very famous in California. But if you now include a new alternative, like the McFadden Special Reserve Pinot Noir at $60, then the perception of people will change. They say, this guy is making reserve wine at $60, so the wine must be good. So if he makes good wine, maybe this is a good deal. And again, this will change. So it's not really a decoy, but you change the perception of the alternatives by doing this. And again, this is something that classical utility theory fails to predict, and that has to be taken into account, again, the perception in this case. This example is about framing. So basically, the way you ask a question may completely change the outcome of the choice. So this is, again, an example from Kahneman and his colleague Tversky. So the idea is the following. So there is a population which is threatened by a disease. You have 600 people in this population, and you are asked to choose between two treatments. Okay, treatment A and treatment B. And then the way you will describe the treatments will be different for two types of respondents. So you have one experiment with one group of respondents, and a second experiment with another group of respondents. In the first experiment, the first treatment is described as follows. If we apply this treatment, 200 people will be saved. And if you apply the second treatment, you will save everybody with probability 1/3, or nobody with probability 2/3. So as you are all mathematicians, you realize that in expectation, it's exactly the same. There is no difference. Okay, so basically the difference between A and B is the probabilistic nature of the treatment. Here it's a deterministic one. And actually, when you present it like this, most people will select the deterministic version of the treatment. Now, the second experiment proposed exactly the same, but present it in a different way. So instead of saying 200 people will be saved, here we say 400 people will die, which is equivalent, right? Because we have 600 individuals in the population. And here the same. So instead of saying 600 saved, we say 0 die, and 600 die with the same probabilities. And again, by changing, it's completely equivalent, right? It's the same, but again, the selection is completely opposite. So there is a significant change in behavior. So this is called framing. The way you ask a question may change the way people respond to it. And so this is something that you need to take into account when you do surveys, when you do this kind of thing. And again, if you want to predict behavior, I mean, this is difficult to predict, right? Because the data are exactly the same in both cases, but the outcome is different. Another interesting experiment that I took from the same book by Ariely is, again, a matter of proportion. So he took these two chocolates, one famous one from Switzerland, and one less famous one from the US. And here, the prices are 1 cent for Hershey and 15 cents for the Lindt. And most people prefer the Swiss one. And now you shift the prices by 1 cent. So you decrease the two prices by 1 cent. So the price difference stays the same. So it's 14 cents versus 0. And now, again, the proportion of people buying the chocolate are exactly the opposite.
It's chocolate for free.
Exactly. So what? But here it's almost free, right?
Unless it's really terrible chocolate. Free stuff usually.
It's 1 cent.
Yeah,
this is 15 times more expensive.
I don't know if I pay 1 cent for Hershey chocolate.
Okay. but if I give it to you, you will eat it. Okay, that's irrational. That's not rational. You don't follow my model. I mean, when we model, remember this probability formula. So it's really the probability that one is larger than the other. Here, the difference between the two is exactly the same. And as you said, I mean, the fact to be free is completely different. Okay, there was when I was a kid, there were, if you go to the supermarket, you get this trolley, and everybody was taking them home and push them in the backyard. Or they were trashed everywhere. And then they started to ask people to put a coin, which was like 5 cents or very small coin, and very below the value of the trolley. But it changed the behavior of people because it tells them, okay, there is a value to this. There is a value. It's not zero. And then people cared about it and bring them back to the supermarket. So the fact that something is a value as opposed to no value, there is a quantum leap that makes a difference. So we should be careful about this, because if we use a classical continuous variable, we may miss this fact that being free means something completely different, in particular to TB. Yeah. I don't think I would, even for free, I would take it. But anyway, we can discuss about it. Okay, and so this is another interesting experiment. It's called the Ultimatum game, and it goes like this. So I have at my disposal an amount of money, it can be $100, and then I'm asking you, okay, I will propose to share this money between you and me, and then you can decide either you keep the deal or you break it. If you keep the deal, it's what I decided that will be implemented. If you break the deal, nobody gets anything. Okay, so I have $100, say that I take $50 and I give you $50. Would you accept? Yeah. Yeah? You like money, huh? So Thibault, suppose that I give you $1 and I keep $99. Would you accept?
No, I keep 99.
No, I decide. The only decision you can make is that yes or no.
Yes, I'm not sure I accept it.
But because with the $1 you can buy the chocolate. So
it's not fair, it's at least 50-50.
No. My deal is that I give you $1 and I keep 99.
Okay, no deal.
You don't want it. Okay. What about you?
I will accept it.
You will accept it. Why?
Because 1 is greater than 0.
Exactly. So why would you reject it?
No, because it's very irrational. It's a question of
so no, suppose that I had told you I will give you $1 without telling you that I would give the. Would you have accepted it?
Of course.
So what's the difference? I mean, because if you break the deal, you don't get anything.
I know, I can't even negotiate.
So any deal, it's not a negotiation. That's why it's called the ultimatum game.
Yeah, you think that you have leverage, but you don't have leverage because it's a single deal, it's a single shot.
Exactly. That's why it's called ultimatum. So who would accept the deal? $1 against 100.
Are you allowed to negotiate?
No.
Are you allowed
No,
to because if you can't say something, you could just say like, you give me $99, I don't accept anything below that. And then the other person has the choice between having no money or having $1.
Yeah,
and
so that's the point. So again, this is why it's called ultimatum. There is one, and actually the share in this room represent approximately the share in this experiment. So most people, if you don't provide more than 30% of the deal, they will reject it. Okay, and actually, if you think about it, if you look at divorce, and that's exactly what's happening. So in divorce, I'm willing to spend a lot of money in lawyers just that my previous partner will not get the money at all. That's really the same thing. So the concept of fairness or equity is something extremely complicated, and which varies across individuals. And yeah, in this case, what you would call rational would not be rational for the next person, which makes things more complicated. So actually, this is basically what's happening. So logically, subject B should be happy with any offer, but because that's money, right? But it does not happen. And actually, it was an incredibly counterintuitive result to nobody but economists or mathematicians. So the humans are not doing what the math says, the humans must be broken. And this is exactly what we don't want to do. So we want to adjust the models to actually predict actual behavior instead of saying people are stupid, they are not following the random utility. Okay, so yeah, as I said, offers of less than 30% usually are rejected because it's not considered fair. So these examples show you that there are things that are apparently irrational, or at least that the classical utility model will fail to predict. But behind this behavior, there is some sort of rationality, actually. Well, people have some perception, or maybe they have some social norms or some attitudes they want to behave. And so the challenge is, can we actually try to take this into account in order to predict correctly the decisions they make? And this is exactly what we would like to do. And we call this a latent concept. So things latent means that we cannot observe, but they play a role in the decision-making process. Okay. So that's what I said. So some observed behavior may appear irrational and inconsistent with random utility theory, but it's only apparent because there is something in the back of the mind of people that for them it looks logical and completely rational to do it. So it's about modeling subjectivity. Okay, and this is where we will include these latent concepts. The problem is to measure them. So an example that you have been working when we did the prediction of the market share for electric vehicles, we could see that some people cared about the environment and therefore were willing to pay more for a car, which is actually more expensive and less convenient than the regular car. And if you really want to predict these market shares correctly, you need to take into account that some people really care about this and it's an attitude that they are really willing to pay more. But how do you know who they are? You cannot just ask them directly. So we do indirect measurements. And the idea, so this comes from a quantitative psychology, these ideas, is that we use what we call psychometric indicators. And the idea is that you provide them with statements, and they have to tell you if they agree or if they disagree with the statement. And actually, usually the scale is on 5 levels. So I strongly agree, I'm neutral, I disagree, I strongly agree. You probably have already filled this kind of questionnaires. This is very common in marketing and in any research involving behavior.
What's the difference between no idea and a neutral?
Well, the idea is that no idea means that you don't understand the question. I never thought about it. And neutral, it means that it's equivalent. I don't agree, I don't disagree. For me, both are. So the idea with these scales is to avoid people being forced to respond something that will bias your analysis. So this is why we always put a way of no idea. I never thought it's not something that I care about. So the price of oil should be increased to reduce congestion and pollution. More example 1. More public transportation is necessary, even if it means additional taxes. Ecology is a threat to minorities and small companies. People and employment are more important than the environment. I feel concerned by the global warming, and decisions must be taken to reduce the greenhouse effect. So 2 comments about this list. First, I'm sure that if you do the exercise, you immediately have an opinion of each of them. It's very easy to fill in, right? So it's something that I agree, I strongly agree. So these kind of questions, usually, it's not even a question, it's a statement. It's very convenient to put many of them in the questionnaires because people, it's very easy to use. Second thing, remember the framing idea that I talked about? So to avoid framing, some of these statements are going into one direction, like more public transportation is necessary. And some other statements are going into the other direction. Ecology is a threat. So for somebody who would care a lot about the environment, some of these would be disagreement and some of these would be agreement. So the reason why we change this kind of phrasing is to avoid framing, because if all the statements were positive, this would amplify the framing that I described before. So this is called, as I said, psychometric indicators. They are usually easy to respond. And I mentioned the importance to minimize framings. And there is no real units, right? So these latent variables, they have no units. It's not dollars, it's not time, it's something which is completely arbitrary. So when we collect the data, we both collect data about the choice people make. So we observe that people have bought an electric car or people are traveling by public transportation. And we also have access to a lot of explanatory variables, the age of the respondent, the income, the price of the bus, everything that matters. So this is what we get for classical choice models, like the logic model that I presented. But in addition, when we want to measure these subjective concept, we also have these indicators here. So this is the response to these psychometric questions that I talk about. So we call the latent variable this subjective concept. So it can be the perception for the Y in this example, like the decoy. In this case, in this example, this is the perception of the attitudes towards the environment. So I denote it by X star. I put star to mention that it is latent. It's a random variable that I cannot observe, but that will play an important role in my model. And because I would like to be able to predict it, I will try to develop a model that predicts your level of attitude as a function of things that I can observe. Age, level of education, you name it. Okay, so this is called a structural equation. It's something that relates a latent concept with things that you can observe, so that you can actually predict for in the future the way this variable will evolve. And once you have a structural model, you can actually include it into the utility function. Okay, so utility is also an observed, by the way. It's also a latent concept. So the way we model utility is like this. So the utility of public transportation depends on the price of the ticket. It depends on the travel time it takes to reach the destination. It depends on the frequency of the bus, but it also depends on the attitudes that the person has for the environment that will influence the utility they have for public transportation.
So maybe my question is a bit too early in the presentation, but later you're going to talk about pricing. And oftentimes when we do pricing, you don't actually know these attributes, right? So what is the underlying assumption on the data availability here? Is it like you have some distribution information of the population that is purchasing something, so that at the very least, you know, sort of the age distribution, the educational distribution, or
no, we have access to the data. So for example, for the electric car example, we have the record data of people who purchase. And you know, you have socioeconomic characteristics already.
But you don't have it of those who did not purchase, right? That you might want to attract in the future.
Yeah, so you need so indeed you need the data to be able to do that. For the prediction, you will work on distributions. You will say in the future the distribution of level of education will be such and such. But to calibrate the model,
yeah, you have it. But
then you need the details. You need to
some distributions for the.
And usually, if you don't have access to the market data directly, you have to do some surveys, stated preference surveys, in order to calibrate. That's usually the combination of the two that makes it. But for prediction, yes, indeed, you make assumptions about the future scenarios. The population will age, will be in the future, maybe the level of education will increase, and then we will see what will be the impact on that. So that's the idea. And it's the same as for choice models. There is no difference. It's just that in addition to the utility, we have now a new latent variable which is included in the model, but that also requires the same type of data to model. And now becomes the fun. So now if I want to predict the probability to choose the electric car or the probability to take the bus, well, now you have the classical variables, price, time, frequency, but now you have this attitude that will play a role. So if I know the attitude of somebody and is the individual, I can use my logit formula, for example, to predict the choice. The problem is that I don't know for each individual what is the level of attitude. I just have my model. So what I need to do is to integrate this quantity over all possible values of the variable here, following the distribution that comes from the structural model. So, and this is where things got complicated, because, well, we are able to estimate these models. But remember, my objective is to include these models into an optimization problem. And when you do OR and you start seeing these integrals, and you are scared, right? This is extremely scary. So it's not only highly nonlinear, it's not even a closed form, it's non-convex. I mean, that's just a nightmare. So that's the challenge. Okay, so if you want to model behavior, in particular subjective behavior, you end up with very complex models. They are sophisticated, they work well, they predict quite well. Actually, there's some validation that you can do, but if you want to use them in optimization, that's complicated. So this is really the challenge that we are facing. So how to deal with it? First, the idea is to say, forget about the probability, because the probability is just a mess. And so let's go back to the first principles that if you remember my first slide, so people, when they make choice, they maximize, they already solve an optimization problem. So let's keep it that way. So if you look at the utility instead of the probability, well, we can basically approximate the choice probability using simulation. So these are random variables. We can draw from the random variable. And for each draw, we can identify which is the best alternative. And then we just count, this is an indicator, we just count how many times, let's say, public transportation is the winner among all the possible draws. And this is a good approximation of the probability. And the advantage is that most of the time, the utility here is a linear function of the variables. And this is better because we can deal with linear specification. So that's the first idea, is to not work at the probability levels because we have this kind of messy formula, but to work at the level of utilities and use simulation to deal with the probabilistic nature of the model. So now I will have three indices. So I is the alternative, N is the individual, and R is the draw that I generate from the distribution. And I have a capital R of such draws, so it should be quite high. Good, so that's the main idea. So now let's try to take this and include it into the optimization problem. Okay, so we would like to use advanced choice models to predict demand and to include this demand model into the optimization model and we will consider here a pricing problem. Okay, and this is something that I'm working with my PhD student and Vanna Lubitsch, who is an expert in Benders decomposition, who is helping us in trying to deal with the complexity of this model. So the pricing problem is not the objective as such, it's just an example of a relatively simple optimization problem. But what we hope is to use what we learned from the pricing problem to actually apply it to other types of optimization problems. So what is the definition of the problem? I have a competitive market, and I have two sets of products. I have J products that I control. I can decide about the price of these products. And K products which come from the competition. I have no control about these prices. Okay, so this is the customers freely choose their preferred product, and we can import any choice models that you see fit for this prediction. Okay, and so the objective is to find the prices of these J alternatives such that the revenues of the operator are maximized. Okay, so that's a relatively classical problem. So the assumptions we are making is that the decision of the competitors are fixed, which is not always the case in a competitive market, because if the market is very competitive, my decision will influence my competitor, and we come into a fixed point. This is not part of this methodology. We use a random utility model, and actually what I did to my PhD students is, okay, you take a model from the literature, right? You don't do any assumption, you take something which has been published and which involves one of these integrals that I showed you. And this is the model that I want you to use in your model. People are different, and this is extremely important. So actually, if people are all the same, the revenue function as a function of price will be concave. If it is too cheap, you will not make any money. If it is free, a lot of people will buy it, but you will not make any revenue. And if it is too expensive, you will not sell much, even if you make a lot of money on one item. So the function is concave. But if people have different tastes, different willingness to pay, different attitudes, as we discussed, the revenue curve will be highly non-concave, because depending on the segment of the markets, you can reach different types of revenue. So this makes the problem interesting and complicated. The utility being the central modeling element in our context, well, we will assume that it is a linear function of price. And this is the case for most models which are published in the literature. So this is really the only assumptions that we will use in this context. And for the rest, the utilities are random variables. We know the specification, we know the distribution. Typically, we take it from a published model in the literature. So this looks like this. So for the controlled alternatives, the utility for alternative I and individual N depends on price. So this is my decision variable, the price vector. Okay, PI is the price of this utility. This is linear in price. And then this is everything else that I can observe. For my point of view of the revenue maximization, this is a constant. that involves everything else that is not price. And this is the epsilon that I'm not observing. Okay, I make the assumption, of course, that the beta is negative, so the people are not attracted by more expensive. So if you increase the price, people will stay away from your alternatives. And for the competitors, you have exactly the same, but there is no price there. So if there is a price, it's also constant, so it will be included in the constant. So the convention that I'm using here is that alternatives from I to j are the alternatives that I control, and the negative indices correspond to the competition. Then I use simulation, as I suggested before. So I draw from this distribution, and I can draw from the beta. So the beta can be distributed. People may have a different sensitivity to price. People with different income, for example, and so on. And the epsilon. So I can draw from it. I can even draw from the constant here. They can be distributed as well. And now I have this specification. Okay. So this is the specification with the draws, and then I can group all the draws together and call it the constant. So basically, for my alternatives, I have two parts. One is the price, and the second one is a constant. It does not vary with price, which basically gathers everything here. And for the uncontrolled alternative, I have just a constant. So this is how the model simplifies in the optimization context. Good. So let's try to formulate with this context. Let's try to formulate the model. So first, let's look at the decision of individuals. Remember, we are optimizing something. We are maximizing the utility. Well, if you look at utility maximization, it's actually a very simple knapsack problem. So I will denote W the decision to purchase or to choose item I by individual N for the draw number R. This is the corresponding utility. Okay, so this is, and I have to choose exactly one. So this is a very simple knapsack problem, and it appears that this has a 0-1 solution. You don't even need to enforce it. Okay, so that's really the interest here, because you don't need to have a constraint to keep the variables binary. So I can write the dual. So the dual basically is to say I will minimize the maximum utility. H is the maximum utility that I will minimize. So this is the dual of this problem. Good. So it means that I will put everything together. So so as I said, the integrality property, it comes from the fact that if the utilities are all different, which is usually the case because you draw from them, and there's always one which is the largest, and this is the one that will be picked up by the knapsack problem. And so these are the optimality conditions: strong duality, dual constraints, and primal constraints. So this is the optimality condition that characterize the choice of the customers in the market. Good. So now I can write my optimization problem. So I want to maximize revenue. I always like to write optimization problem as minimization, so but that's equivalent. So I put the minus. So this is actually the revenue. So it's the sum for all the draws, all the individuals, and all the product that I control of the price, which will generate a revenue if people choose it. So if W is 1. Okay. And so this is the total revenue. And you recognize here the optimality condition of the customers that I presented in the previous slide. And this is just the definition of the utility. Okay, so this is the problem I want to solve. So let's make some simplifications. Because the two main difficulties of this problem is the one is that it's nonlinear. It's the product of two variables here, the price and the. So this is like the supply variable, and this is the demand variable, and they interact by a multiplication. And the second issue is that if R is large, this is a huge problem. I mean, you have a lot of constraints if you have a lot of individual and a lot of duals. So these are the two difficulties that you are facing: the nonlinearity and the high number of constraints in the specification. Well, the first simplification comes from the fact that, well, if you look at these constraints, among all the competitors, the only one that actually matters is the best one for a given draw and a given individual. Why? Because this will be the main one I will compete, and because it's constant, the others will not matter. So for each M and for each R, I will identify the best competitor, and this will be my competitor for this draw and this. So I will be able to basically remove everything else. And actually, instead of having like K indices here, I will have just one that I will call 0. And this is basically the opt-out option. So if people don't want to buy my product, they go to the competition. This will characterize the competition. So this will be simplified. So I define the C0 now as the best, the maximum of this constant. And this is what will enter in my model. So now I have this specification. Okay, so for my alternatives, it's like before, and now I have this opt-out option. So this reduces the size of the problem by this. And now I will explicitly substitute these quantities in my specification. And then I will capture the nonlinearity by a new variable, eta, I, and R. That will be the variable that is the product between the P and the W. It's the contribution to the revenue for alternative I, individual N, and draw R. And then I obtain this. So this is the same problem where, as you can see now, I have substituted the utilities, okay, explicitly. And I have now this eta variable, which appears here. So then the only place where there is no linearity is at this definition here. That's everything else is linear. Yep.
I have a small question. Is the number of N and R is like sufficiently small so that you can compute C, O, and R and W? The opt-out option, can you compute the maximum value beforehand, or you have to do
it's beforehand? Okay. This is beforehand because this is constant. It does not depend on P. So the rest of the market, they have made the decision. So I have access to the full utility function, but actually I care only about the best of them, which can be different from one draw to the next. So this is why I have this R here. So maybe for the first draw, this is one guy who is the best, and for the next draw with another one. But it does not matter. This is why I need to calculate this beforehand. So this is not varying with the inside the optimization.
Okay.
Emma?
In the formulation that you showed, we did not have any capacity constraints, right? So you have infinite supply. Otherwise, these simplifications would not be possible.
No, that's not true. You need an opt-out option. It's not the optimal solution is infinite price. Okay, and the capacity constraint is only on your alternative solution because this is what you decide. So usually we don't care about capacity constraints on the competition. We just see the competition as everybody else, and that's so. But that's a good point. So right now, explicitly, we don't include capacity constraints because I will come to the decomposition of the problem in a bit. Capacity constraint is a very strong linking constraint that we don't put. So the challenge is to first understand the structure of the problem in a simple context, pricing, without capacity. And so we have made some experiment with capacity, so it's more complicated, and it's not included in this. Good, so the next step is to simplify even more the problem is to include valid inequalities. Okay, and what we have done is to deal with the so-called McCormick envelopes in order to deal somehow with this nonlinearity. So remember, the nonlinearity is due to the product of Py and Wi and R, and each of them are bounds, are constrained by bounds. So these are the bounds of the price, and this is the bounds of the 0, 1 variable. So you can actually, I assume you know about the McCormick. So these are valid inequalities. And basically, you can multiply them pairwise, and then you get these nice inequalities on the eta. So this is linear inequalities that link the eta, the P, and the W. So putting everything together, these are the McCormick valid inequalities. But remember, we are trying to maximize revenue. So the lower bounds, we don't really care because the eta will be attracted by high values. So we will keep only these two constraints in the specification. The second one is more driven by the utility concept. So suppose here I have the case of one product, the price that I control. And so this is the utility for this individual and this draw. So that decreases linearly with price. Okay, so this is the utility as the y-axis and price as the x-axis. And this is the opt-out, my competitor. Well, clearly at some point, I will cross this breakpoint. And the breakpoint is where people are indifferent between my alternatives and the opt-out option. If my alternative is more expensive, I will lose the customer. And if it is cheaper, I will lose revenue somehow. Okay. So this breakpoint is very important because this is where things happen. This is really where. So if I want to maximize my revenue just for this guy, so N and R, the optimal solution would be here. And actually, if you look at the same draw with the eta, which is the contribution to the revenue, so if I increase the price, I will increase my revenue up to P bar I, at which point I will drop everything. I will get 0 for this specific N and R because they will go to the opt-out option. So, well, there is one obvious valid inequality, which is the fact that eta is bounded by the price. That's trivial. So this is, but there is another one that I can put here, is to draw this line here. And somehow this valid inequality will tell my model that if you overdo it with the price, your revenue will decrease and eventually will become 0. Okay, so this is the valid inequality that I can. It's valid because any value will be below the line, and at some point it goes to 0. So again, to tell my model that I will be driven away from it. So this is it. And now I can generalize it to more than one. So if I have several prices, I can take them 2 by 2. So I will not go through the details of the equation, but this is exactly the same idea. You look at the indifference line and you make this the same type of value inequality. Okay, now how do we deal with nonlinearity? Well, the best thing we have found so far is to use a spatial branch bound. Okay, so you start with a reasonable interval of prices, and then you split it as you go along in order to narrow it down. So we relax the nonlinear constraints, okay, and we work with the relaxation in the context of the spatial branch bound. So each time you solve the relaxation, you get an upper bound, okay, but then you can use this price and look at the behavior of people. So you can calculate the utilities and calculate the choice. So it means that you can also, by using the price, which is the solution of the relaxation, you can find a feasible solution because it's easy to find a chosen alternative. It's the largest utility. So it gives you a lower bound for free somehow. So this is the advantage here. Okay, you solve the relaxation, you get the upper bound, and you get also a lower bound, and then you split the price interval and you start with.
I have a question. So your WINR, ideally it would be a 0-1 variable.
Yes.
But you took it as continuous at the start.
Yes.
And that's why you need to introduce a spatial branch and bound kind of a scheme. So if you had kept it 0-1, then you would not need to. You would get an exact reformulation, right?
No, because you still have this nonlinearity.
Yeah, but this can be you can get a linear reformulation because it's one variable in binary, so you can call it X.
Oh, yes.
The big M.
You mean the W is being imposed, but then you lose the strong duality constraint that I had before, right? So that's really the trade-off that we have here, and we tried with big M constraints to do that, but they are really bad, and usually big M constraints really driving you away from a lot of things. And as I will show after, we will try to use benders. And then you forget about getting duality from benders if you do that. So yeah, that's the problem. So how to deal with the large size? So this is what I was talking about, the benders. So again, if the prices are fixed, this is easy. You can actually identify the choice of everybody by fixing the price. And so this is really natural to consider benders because it's highly decomposable. Okay, so the complicating variable is the price, and you can define a bender subproblem for each N and R. So you probably know about benders. So you have a master problem, which is the price here. Okay, you provide candidate solutions to the subproblem. So you fix the prices. People make the decision, and then you generate cuts, optimality cuts, to refine the master problem in order to converge hopefully to the solution. So this is the bender subproblem. So for each N and R, we want to maximize the revenue, and this is the same specification that we had before. And here, I impose the price to be equal to the candidate that was provided by the master problem, and the dual variable associated with this will be used to generate the cut at the master level. That's what I think. So phi is the dual variable of the subproblem that I can Okay, so this is really what we have tried to use, and I will quickly show you some numerical experiments. Well, the bottom line is that it works okay, but we would like it to work better. So the challenge was, as I said before, I told my student, go to the literature. I want a published paper, a model from this paper, and this model should be involving an integral. So this is parking choice. So we have two parkings, one on street and one underground, and we have to decide about the price of these parkings. And the opt-out option is the free on-street parking. Okay, so that's the idea. And these are the computational results. So one challenge is to see how this scales up with the number of draws, because when you use simulation, if you want a good approximation of the choice probability, you need R to be large. And here we compare basically solving with Gorobi the main problem. This is the first one. This is the branch and bounds formulation that I showed before with this relaxation that we, and this is the one with benders. And this is where I said that this is really good news because we can actually, so this is the runtime. Okay, so we can afford, thanks to benders, to go to relatively high values of R, which are actually sufficient for most applications. So this is, it means that we are getting something which is operational. Now, if you look at the optimality gap, this is also very good news because we are basically able to solve it almost to optimality. So remember, we have the lower bound and the upper bound. So we close this gap. And here we are able to close it all the way to 7,000 draws. While here, starting from 2,000 draws, we are not able to find an optimal solution anymore, and Gorobi stops even finding a feasible solution at that point. Okay. So we are going in the right direction. So this is good news. This is another case where I have two prices now. The previous one was one price, and now we are able to go until 3,000, and then it deteriorates starting 3,000. So we still have some improvement. And this is a long table that Tom sent me, which basically tells you the same story as before. I will not go through this. Something that was interesting, he was trying to identify the contribution of each of these ingredients that I presented. And unfortunately, it seems that the valid inequalities are not playing a good role. And I believe it's an implementation issue. I think we have a lot of constraints to deal with. And so this is something that is currently investigated. But the benders, of course, played a very huge role in the running time, and also the simplification that I told you about removing the irrelevant alternatives and so on. Good, so let's conclude. Individualist behavior may appear irrational, and this justifies the use of advanced choice models, which have a complicated mathematical formula. So this works, these are operational, but at the expense of more mathematical complexity. So the challenge is to integrate these models into optimization. And the way we have decided to try it is to go back to first principles, see the optimization problem that people are solving, writing it explicitly and including it into the optimization problem, as I showed you in the example of the pricing problem. Okay, so this was the example that I showed. And of course, and this statement is true for any problem that you have to solve, you need to exploit the structure of the problem. So this idea of breakpoints where people switch the decision is extremely important in this specification. So we are currently trying branch and bound with benders. There are other possibilities. We will investigate also column generation. We have tried Lagrangian relaxation before, it didn't work well. Okay, but so far it's very encouraging because we are really able to solve large instances that Gorobi cannot do. So this is very encouraging, but there is still some work. So the slides are available online, and I've included all the references, in particular the book that I was talking about. So you can good. So I'll stop here, and I'm happy to address more questions if you may. Thank you.